The last video showed a perfect instruction pipeline, but there was also an example with a pipeline stall that delayed execution. There are three types of hazards or bubbles that can cause a pipeline to stall. These are resource hazards, also known as structural hazards, and then there are data hazards, and then finally there are control or branch hazards. We saw a resource hazard in the previous video where limited human resources meant that I could not fold and gather laundry at the same time. But what can cause a resource hazard in a processor pipeline? Let's consider a simple computer with only one interface to memory via the bus. Here is an x86 instruction that moves the contents of the memory address that correspond to the value in register EBX into the register EAX. So these square brackets mean we're doing a memory reference. Now here, I've laid out the pipeline stages, but I've actually added a new one that wasn't in the previous video. So before we had fetch instruction, decode instruction, fetch operands, and then we also had execute instruction and write operands. But the one I've added here, IN for indirect, means we're doing an indirect memory access. So here we're fetching the operand EBX, but then we do a memory lookup in this phase that goes to the address corresponding to the value in EBX. So this is a new 6-stage pipeline, and we're going to see that being able to access memory here causes problems. Now, as I mentioned, we're assuming a simple situation where we only have one interface for memory access. So we're accessing memory via this instruction here. We're pulling data from memory on this stage of the pipeline, but we also access memory when we fetch the instructions from memory. So what happens when we add more instructions to this sequence? So I've written out the pipeline stages for the next two instructions, but not for this last one. So for these instructions, the pipeline just fills out in the optimal fashion because there are no conflicts. But at this instruction, we would like to fetch that instruction here. But this particular instruction, because of those square brackets, means that this in stage of the pipeline is accessing memory. And assuming we only have one memory interface, that is a resource conflict, a resource hazard. And so I can't fetch the instruction here. And instead, that gets pushed over one pipeline stage, and then everything gets laid out from there. Generally speaking, the easy way to avoid resource hazards like this is to duplicate hardware. So I could have two memory access pathways instead of one. Of course, extra hardware takes up valuable space on the processor chip and costs more money to manufacture. So we've discussed resource or structural hazards. The next one we'll talk about are data hazards. Data hazards occur when the results from calculations are not yet located where they need to be. Consider this example. I've written out how the pipeline gets filled for the first two instructions here. The first instruction changes the value of EAX, but that change doesn't take place until the write operand stage of the pipeline. So until we reach this point, the value of EAX has not been updated. Similarly, the second instruction changes the value of EBX, and that value has not been updated until this write operand stage occurs. Now, for this final instruction, I'm adding the values of EAX and EBX. And since this occurs after those two instructions, I clearly mean to add the modified values. So whatever these got changed to in the previous two instructions, that's what I want to add on this third instruction. So I can still fetch the instruction at the usual point and decode it at the usual point. But when it comes to fetching the operands, I can't fetch operands here because those registers haven't been modified yet. So I have to stall until both of them have been modified. And at this point, I can fetch those now modified operand values and continue with the rest of the pipeline like so. This specific data hazard is an example of a raw hazard or a read after write. You see that each of these registers were written to here, and the read occurs directly after it. So we have a read after write hazard. Other possible hazards include write after read and write after write. But these are usually not a big problem. A write after write means that you can modify a register and then modify it again, but usually only the final value written matters anyway. So this is really only a problem if you have variable length instructions, which can happen in some pipelines, but not in any examples that I'll show. Similarly, write after read problems are also rare. So we're mainly going to be concerned about read after write data hazards. So that takes care of data hazards. The final type of hazard we'll discuss are control hazards, also known as branch hazards. These occur when you have a jump or a branch in the code. Specifically, we care about conditional jumps or conditional branches like the one we're seeing here, JL for jump less. So there's a comparison here between these register values, and we will only jump to some label down here if EAX is less than EBX. Now, pipelines fill with instructions before previous instructions finish. So the processor needs to know what the next instruction is. But this is hard when there's a conditional jump. Should the processor load the instructions assuming the jump won't occur, meaning it would load these ones? Or should it assume the jump will occur, meaning it will load this instruction after this jump here? Branch prediction and the associated topic of speculative execution are complex topics in their own right, but we're just focused on pipelining right now. So let's just assume that a processor's default assumption is that a conditional jump won't occur. So for this code, we'll simply load the instructions after the jump into the pipeline, which looks like this. So instructions after the JL command are loaded into the pipeline. And if this jump doesn't happen, then this pipeline is good because we have already started executing parts of these instructions that happen after the jump. And so by the time we know the jump happens, which is when the EI or execute instruction phase happens, so this is when we know whether the jump has happened, we'll have already done all of this useful work. And we can continue carrying out the rest of those instructions, even up to the point where we reach this instruction that comes after that jump label, which for this specific example, we're either going to do it here after those instructions or jump straight to it. So this is what happens if we don't do the jump. Now, if the jump does happen, we will still have loaded these instructions into the pipeline. But in that case, this work we've done here was actually wasted. And so as soon as we realize that, which once again occurs at the EI stage of the jump instruction, we have to flush the pipeline, get rid of all of the wasted work, and then go straight to this point where we'll continue from. So the pipeline flush looks like this. We know that none of this is going to happen, even though we were planning on doing it. So this gets flushed out. Now, this work we've done here, this is wasted effort. So we've already started executing parts of these instructions here, but unfortunately, it turns out that these instructions didn't actually execute. They weren't meant to execute because this jump skipped over to this point here. So none of this really happened. But fortunately, none of these stages have modified any data yet. So we don't have any problems by simply, you know, skipping ahead and ignoring what's happened there so far. We also have these two instructions, which would never have been loaded into the pipeline in the first place because we can only go so far ahead with our pipeline. And these instructions were so far in the future that by the time we knew we were doing the jump, we wouldn't have even loaded any part of them. So we would jump straight to this instruction, and actually, this would be shifted back slightly. So the stages for this instruction would start right here where this other instruction left off. So by getting rid of all of this, we get to move this up a little bit in time, and the result looks like this. So what we're seeing here is the sequence of pipeline stages that were actually executed as opposed to how they're laid out in the static code. So in terms of instructions, this instruction executed to completion, this one executed to completion, and then this one executed after that. None of these executed to completion, but portions of them did execute in the pipeline. And so we're seeing which pipeline stages for each of these instructions actually executed, and we see that nothing actually happened here. We had planned to execute more stages of these instructions, but that got flushed out, and we just jumped straight to this one, completely skipping over the additional instructions that were between here and here earlier. And with that final type of hazard removed from our list, we have covered the basics of pipeline hazards. Of course, things can get a lot more complicated when multiple types of hazards are interacting with each other. And there's also a lot of clever ways for dealing with the code to make hazards less likely. And perhaps some of that will be covered in a later video.